a big production out of this, but I botched the end of class yesterday, as you can tell. Cameron, are you actually
I'm
on?
now on, yeah.
You're on, okay. So I want this on the video more than
Yeah,
anything.
that's what I figured.
So I got myself bamboozled a little bit at the end yesterday. It really is quite simple to finish up where we were with the uniqueness argument for reduced echelon form, but we're moving on from there. All right. So some of you have already been Googling and Wikipediaing and have apparently discovered that there's some connection between non-singularity of a matrix and invertibility. So that's what we're going to talk about today. So I want to stress here that you have two very different looking definitions. So we're talking about square matrices, and we say it's non-singular if what?
Rank is less than the number of
Rank
is equal to rank.
Oh, rank equals n.
Non-singular if the rank equals n. And I'm going to comment, although I didn't say this yesterday, that's equivalent to saying what about its reduced echelon form? It's the identity. Does everybody see that that's right? You have no rows of zeros in your reduced echelon form, and it's a square matrix. Then you've made all the pivots ones. There's a pivot in every row, but there's also a pivot in every column because they're equal numbers of rows and columns. So you have everything cleared out except for the ones. That's the identity matrix. Okay. Now go back to chapter 1. What was the definition of invertible?
Determinant is not equal to 0.
No.
There's an inverse matrix.
There's an inverse matrix. So there is an n by n matrix so that A times B is the n by n identity, and B times A likewise is. Offhand, these don't look like they're necessarily related. But let's think about this. Do we have a different characterization of non-singularity?
They have a unique solution.
Right. So you used in your homework a lot the fact that you could characterize, whoops, I was writing what I was saying and not what makes sense. You can characterize a matrix A as being non-singular in two different ways. One is that the homogeneous equation AX equals 0
Has a unique solution.
has only the trivial solution. And what's also an equivalent way of saying it, that if you take
AX equals B.
an inhomogeneous equation, AX equals B,
Has only one solution.
it has a unique solution for every B. So this is what we discussed the last few days, thinking about rank, free variables, consistency, all those things put together. So let's see if this actually helps us figure out something about what's going on here. What does it mean to say, so at this point I'm going to erase this, what does it mean to say A times B is the identity? So you have an A, and you're multiplying it by a matrix B, and you're getting the identity.
Is it the ith row of A times the jth column of B is column or whatever? Or is that not what we're doing?
You're sort of close. But go back to how we first defined matrix multiplying by vector.
Isn't that I, like, is like the ith row, the ith row in,
Yeah, don't worry about rows of A, is my hint.
Yeah, it's just the fact
But how do we interpret matrix times matrix? We think of it column by column, do we not?
dotted with
So if you multiply A by the jth column of B, what are you getting? EJ, right? You're getting the jth column of the identity matrix, which is the jth standard basis vector. So in other words, finding this matrix B is a matter of finding vectors that solve A times
X equals EJ.
whom equals EJ for each J. So let's see. If A is non-singular, we just said that there is a unique, now my notation sucks, pardon my language, but, so rewrite this without the letter B there. Here's a different letter. And here's your C. Here's your vector in Rn. And we're saying there's a unique vector Bj that solves this equation when A is non-singular. Thus, if A is non-singular,
There's only one matrix B.
there is a unique such vector Bj for each J going from 1 to n. Right? Non-singular tells you you can solve this equation for a unique vector for each of the standard basis vectors. That means you found a B that satisfies A times B equals the identity. So it looks like we've shown that a non-singular matrix is invertible. But have we really? I haven't shown you this. Now, let's actually try to do a numerical example of this. How would you actually, in real life, solve A times somebody equals vector? What would you do?
Use matrix algebra.
Row operations.
But row operations with what?
In your augmented matrix.
Augmented, right. So normally if you wanted to solve A times X equals C, you would take your augmented matrix
and then reduce.
and you would reduce it, and since in this case A is non-singular, you know you get the identity as the reduced echelon form, and whatever you have here would be your solution X. Maybe I shouldn't call it X, let's call it S for solution. Right, you would actually literally read it off. X1 is this, X2 is this, X3 is this, because you have the identity there. So this means that S solves the equation A times whom equals C. I want to do that for each of the standard basis vectors. That means I have to do n different row operations, turning A into the identity n different times, just having different right-hand sides. That sounds tedious.
Do it with the generic.
So I'm actually going to put a matrix on the board now. So let's say A is this matrix, which I hope I have no typos in. 2, 1, 1, 1, 2, 1, 3, negative 1, 1. So I say to myself, I'm going to try to do this algorithm. So I'm going to augment A. And then I'm going to put E1 here. And I'm going to row operate and find my solution. And then I'm going to go back and start all over again and put E2 here. And then I'm going to go back and do all the row operations. And then I'm going to go back and do a third one where I have 0, 0, 1, and I do all the same row operations.
Can you just
do it.
Can you think of a better way?
Just do a generic C
Do-
and
yeah,
C
just-
variable.
Zeros.
The identity, right? Put the identity matrix in.
So you could put arbitrary letters here and do it, and then just substitute at the end. But that's more writing than it's worth. So what you should think about doing is augmenting all three simultaneously. But it's customary, and then just do the row operations once. And as you do that, you track them all simultaneously. Now so this would be a super augmented matrix.
Is that a technical term?
No.
Why?
But it's customary not to put the extra dots in there, dashes, and just stick the matrix next to the first matrix with the dotted lines here. And notice, of course, the matrix whose columns are the EJs is, of course, our identity matrix that we started with on the right there in the first place. So you're going to start with your matrix, you're going to put the identity matrix next to it, and then now when you reduce to reduced echelon form, because A is non-singular, we're getting the identity, and then this guy is going to be our matrix B. So let's just do it. So help me do this. What should I do to get this to reduced echelon form?
Let's put the middle row at the top.
Yeah,
Should we switch rows so that we have a 1 at the top?
Yeah.
Okay. So you have to do everything on both sides of the matrix now. 2, 1, 1, 1, 0, 0, 3, negative 1, 1, 0, 0, 1. All right? What's next?
Let's get rid of the 2 and the 3.
Get rid of the 2 and 3. You have a pivot here. Use it to clear out below. So I'll write the first row back. But be very careful not to just be on automatic pilot. Make sure you write the correct right-hand side. Okay? Read me the next row, Dan. And then somebody else is on.
Oh, 0. I'm going to say negative 3.
Negative 3.
Yeah. And it's either 1 or negative 1. I'm going to go with negative 1.
And what happens on the right?
Oh. Start with a 1. And then it's negative 2.
Okay. The 0 is still there. All right. Dan wore out. We need somebody else. Tori, you want to help me with the last row?
It's okay, you're really pretty.
So I want
I
to
said it's
kill
okay,
the
you're
3.
really pretty.
Negative 1 minus 6. So,
Subtracting.
and then 1 minus 3. Negative 2. And what happens on the right? 0, negative 3, 1. Right, so we were adding negative 3 times the first row to the last row. Now what do I do? Yuck. We had something like this 3 days ago. So first of all, you might want to get rid of all the negatives. Is that something you'd like us to do? Because you guys aren't good at negatives.
Yeah, let's just talk about everybody.
I mean, Dan is good at being negative.
Oh.
I can walk out that door if you'd like.
All right, so I multiplied the second and third rows by negative 1. Maybe I didn't need to do that, but I did it. But I don't want fractions with thirds or sevenths. What can I do?
Multiply the 0 by 7 and the bottom
Louder, Mallory?
multiply the middle row by 7 and the bottom.
Whoa, no, I
Why
like
don't you
that.
just take 2 of the second row and then minus?
Right, combine, you can take -2 of these and add it to this and you'll have a 1. Remember we did this, an example of this the first day, and I told you it's a useful technique. So I'll leave the third row the same, for the second row for the same for the moment, and then I'm going to add negative twice this to this. 0, 1, 0, -2 of these, -2 of these plus this. Looks like I have that.
Wait, should that be a negative, or should that be a 3?
So I added -2 of these to this,
Yeah.
-2 of this to this, -2 of this to this,
Oh, okay, sorry. I thought you
-2 of
were-
this to this.
Okay, yeah.
Now what should I do?
Switch 2 and 3.
Well, how about we
Swap the
How about we
bottom.
switch rows to obey our rules? So 1, 2, 1, 0, 1, 0, 0, 1, 0, 2, -1, -1, 0, 3. Yeah, so I'm not going to skip steps. In the privacy of your own notebook, you might have combined a step here. Now I'm going to do what? I'm going to use this pivot to kill.
Top and bottom.
I'm not going to kill top yet, and I'll make a comment in a minute. I haven't made this comment yet, so I will in a minute. I'm just going to kill below first. So how do I kill below? Add -3 times the second row to the last row. -3 of these to this. Go for it.
-7.
Negative 5, 3.
Okay. Now, I'm going to use this pivot first to kill off above. It didn't matter so much for this example because there was a 0 there, but I'm going to tell you in practice that you should first go to echelon form, and then, starting at the right, clear out above. You will do less arithmetic and have fewer chances of errors if you do that. Because if this hadn't been a 0, I would first clear it off before I tried to use this row to kill up this, and that would make the arithmetic one step simpler. So if you actually try a few problems in practice, you'll see what I'm saying. So I want to use this one now, starting at the right. I want to use this pivot to clear out above, and then I'll use this pivot to clear out above. So I'm going to kill there. There's nothing to kill in the second row because it's already a 0 there. 2, -1, -1. And now what do I have for the top row here?
7, -4.
I'm adding negative this row to this row. 7, -4, -3. Okay, and now we're at the last step, where we use this pivot to clear out above. So the final step is going to be, yippee. The bottom row doesn't change, the second row doesn't change, and now I add -2 of the second row to the top row, -2 of these to this. What do I get?
3 minus 2 minus 1.
Everybody agree? So you might want to practice a couple of these. Webwork will no doubt make you do one. Yes, you can cheat and use Mathematica or cheat and use your calculator, but you better make sure you know how to do this by hand. So practice a little bit. So here's my B, and what we know is, unless I've screwed up, but you were all helping me, so if I screwed up, you're all to blame.
You taught us.
To make mistakes. So by construction, the original A multiplied by B is the identity. That's how we came up with this algorithm. But then you might ask yourself,
then just multiply it.
You could just do the
So what do you
same.
mean work backwards?
Just multiply it.
You could do the same
Yeah.
thing, but
Check that it works.
We have AI, but now we have BI.
Try to find
So
B
it's
yeah, you could do the
similarly,
same thing with BI to try to get
B
IA.
times A equals I.
Okay, so
Do the same thing back.
you guys, so very good, you guys. So you don't want me to actually sit and multiply it out. You want to make some
Just by
abstract
construction.
argument. So Alex has just come up with the argument that one of my students came up with some years ago that I had never seen in any books, so I'm proud of you guys for seeing this. What Alex is telling me is that if we started with A in the identity, we row reduced it to the identity and B, and he's saying, just stand on your head and look upside down and start here.
Do the same row.
And do row operations backwards, and you've turned B into the identity, and you've turned the identity into A, so what does that tell you?
A is the inverse of B.
A works on the right for B, right? We said when we do this algorithm, we're solving this matrix times what equals that matrix. So now if you think of it upside down, you're saying this matrix times what equals that matrix. B times what equals I. Well, that's the solution. So if you look at the algorithm upside down, it's telling you that in fact the other equation holds as well.
And this is because
It's a very cute argument, and I'm proud of you for noticing that.
that's because like row operations are like invertible, right?
That's right. So all the row operations can be reversed. Well, I'm going to talk about that explicitly in a few minutes. So this is one very clever argument. And again, as I said, I'm surprised the first 10 times I taught linear algebra, none of the books that I taught out of had that argument in them. So I don't know why more people didn't notice it. Okay, so we have now proved what? We've done an example, and we actually have proved that if it's non-singular, then now, I will show you another way of doing that clever argument in a few minutes, but I want to finish. So we've shown that if you're non-singular, then you're invertible. What about the converse?
Yes.
Yeah.
Can you prove it to me easily? We said non-singularity was characterized by these critters. Can you use invertibility to prove this?
Can you reverse the argument?
Specific.
Suppose A is invertible.
Then there's only one matrix that is a candidate for an inverse, right?
Or we actually haven't proved that, although we could. But I want to prove a matrix is non-singular. How did you do it 3 times in homework?
That there was only the trivial solution to it.
So suppose you have AX equals 0. And you want to solve for X and show that only the trivial solution holds. How do I use that A is invertible to solve this equation? We did that back in chapter 1. Multiply by A inverse. Well, A inverse times AX is A inverse times 0,
Which is going to be 0.
which is 0. And this side is X. So X has to be 0. So if A is invertible, the only solution to AX equals 0 is the trivial solution. Thus, A is
Non-singular.
non-singular. So, in fact, the theorem is these are equivalent. Now, I'm warning you right now, and we have a witness who will testify, that on the final exam, I will ask you to give me definitions of these two terms. And don't you dare
Say that they're the same.
screw up the definitions because we've proved a theorem that says the two concepts are equivalent. We have a theorem that says these are equivalent concepts, but the definitions are very different. So stating a definition is not the same thing as stating a theorem. So if you give me that the definition non-singular is that it's invertible, you will get 0 points for that problem on the final. Got it?
That's the answer right there.
Subtle, wasn't that?
You used to just write important on the board for us.
Well, I've done that a fair amount this term too.
Okay. Kids have it so easy.
Now, I feel obliged at this point to make a comment because something came up in chapter 1 and you asked me about this. So let me now address it explicitly. If A is square and A, let's say B times A is the identity, can we conclude that B is the inverse of that?
What if they're both the identity?
Well, I don't know they're both the identity. Maybe I'll start with the other one first.
Wait, if
B is singular.
Hmm?
B is singular, not necessarily.
Well, could be B singular.
What?
So do you understand what I'm asking here? I'm saying you only have half the definition of inverse, which is sort of where we were earlier. Can you conclude from this condition that A has to be non-singular and therefore invertible? So if you knew A had to be non-singular, could you conclude it?
Wait, did we just do
yeah,
that?
Could you conclude? I don't know, did we?
this,
Yeah,
doesn't it just imply that BI equal, it reduces to like the augmented matrix of BI, like reduces to IA, and then therefore the other way around?
Oh, I see. So you're interpreting it from the proof we did.
Or yeah, like the what about the A up there?
So you're saying that if you started here with B and the identity and you row reduced it, this equation would say that this had to be A.
And therefore using the proof, same thing goes there.
Yeah, so from the proof you can deduce it.
Could you just multiply by A inverse on both sides?
Yeah, so, okay, right. So what I was trying to get you to do is reason more from general principles. If you knew A was non-singular, we've just proved it's invertible. So if A is non-singular, we've proved it's invertible. And now what can you do with this equation if you know A has an inverse?
Multiply by A inverse.
On both sides.
Yeah.
To the left or to the right?
To the right.
To the right.
Okay.
I have qualms about this.
Well, you're supposed to have a qualm.
If it's just square, we
Not
don't.
more than one qualm, but you're supposed to have a qualm.
Okay.
If it's square, we don't necessarily know it's invertible then. Is that what you?
Non-singular.
Well, yeah, but for your top question. So-
Well,
What
so,
do we do?
What if,
So
what
phrase
if,
it
what if
A is the identity,
okay.
and B has,
If A is the identity, the only way this can happen is for B to be the identity.
A is
because I
zero.
know the identity.
Just look at the equation. B times identity equals identity,
no,
so B equals identity.
And that
But-
would be is it like inverse?
if this is 1, and these are all zeros, you get a 1 there.
I have no idea what you're talking about.
I'm working through it in my head.
Do you want to?
You can go on without me
If
if
there's
there's.
an identity.
But the qualm that Dan meant to have is we did this step stipulating that A was non-singular. Can you infer that A is non-singular just knowing this?
Yeah. We can,
Allison, you think no?
we can infer, we can
No.
borrow when we infer.
Can we? Yes, should we?
I'm not passing moral judgments on you yet, guys.
Is that next chapter?
What did we say were the criteria that were equivalent to non-singularity? Only trivial solution of.
Yeah.
So suppose you had this equation, and you had the equation AX equals 0. What could you do with this equation? Could you solve for x?
Sure.
Isn't that what we just did here? Couldn't you multiply this by b? Right? And then regroup, and you get, this is the same as BA times x, which is the identity times x, and so you proved x has to be 0. So if you have this equation, A has to be non-singular. This is sometimes, by the way, in the land of non-square matrices. I've assigned this as a challenge problem. It's not particularly challenging, but I didn't want to give you too many homework problems this week. Even in non-square matrix land, if you have something that looks like an inverse on the left, it's called a left inverse. It looks like an inverse on the right, it's called a right inverse. And if it quacks on the left and it quacks on the right,
It's a duck.
it's an inverse, it's not a duck.
I didn't know inverses could whack.
What about the other way around?
Have you studied biology?
Suppose A is square, and you have a right inverse. Well, let me actually call it C. Can we conclude C is A inverse? Do you think you could do it if you knew A was non-singular?
Yes.
Well, do you think you can use this to show A must be non-singular?
Yes.
Can't do it the same way I just did it, though. How do you use AC equals I to deduce A is non-singular?
Could you do the thing we did in the proof of there where you write AX equals B as a unique solution and then the B vectors make up C?
You're very close to being correct, but that's not quite right.
Could you use the idea that if you have like AFC of AFC of x equals 0, then
Well,
But we don't know that C is.
You set
You-
you set the identity as A, because yeah, A times A inverse.
well, we don't know A is invertible yet. We're trying to prove A is invertible. But suppose this is true. So I think we're,
if you multiply both sides by x on like the right,
well, don't use the letter X.
or 0, sorry.
Don't use 0 either.
Why?
Why? Maybe you meant Y, not use 0, but I put a Y. What does this tell you?
AC has to equal the identity.
No, we already knew AC was dead
It
end.
has a unique solution for every Y.
Ah, so I can regroup. This regrouping stuff is huge, guys. What does this tell you?
C, Y,
Bryce, you see that this is almost where you were?
Kinda, yeah.
Given any y, what have you shown? You've shown that you can multiply a by this vector cy and get y. So do you have a solution for ax equals y for every y?
CY.
That's characterizing non-singular, right? Thus, for every y, we have an x, namely cy with ax equals y. Therefore, ax equals y is consistent for every y. What does that tell you about rank of A?
R equals.
Because if the rank were less than n,
There could be.
there would be things for which it was not consistent. You would have constraint equations for consistency if the rank were less than n. So this means A is non-singular, so the proof works too. So we're just playing games here. This is a little bit of symbol pushing, which is not my favorite thing in math, but it's all based on the concepts of understanding different ways of thinking about rank in terms of consistency and uniqueness of solutions. Okay, any questions on this? So I now want to spend a little time interpreting row operations in a different way, and it will give a different way of proving this result here as well. This will be important for us, particularly when we're studying determinants next semester, but it's actually rather neat, and I think at first you're going to not like it, but then I think you'll end up liking this. So here's an alternative, I wouldn't say approach, but I just did. I want to think about taking a matrix, for example, and let's not have it be square. Let's have it be not square. And suppose I wanted to do, we have three kinds of row operations. What kinds of row operations are there? Switch rows. All right, so what I want to do is ask myself, can I write down a matrix E so that when I do E times A, I get the matrix A with the rows switched? Can you give me an E that will do that?
0, 1, 1, 0.
So Jonathan's saying, write the identity matrix. By the way, first of all, A should be 2 by 2, right? Because A has 2 rows. So if you think in terms of fingers, you need 2 columns here. But then you want the answer to have 2 rows as well, so it has to be 2 by 2.
And then switch the rows to the identity.
Switch the rows in the identity matrix.
Whoa.
Now what happens if I multiply this matrix times my original A? Use your fingers, what are you doing? You're taking 1 of what's in the second row for each time you do it. And then when you get to the second row, you're doing 1 of what's in the first row. So when you do this, you're taking the rows of A and you're switching them. This is analogous to doing what? Multiplying a matrix times a vector and doing columns added together according to those coefficients. Now we're doing it with rows. We're thinking about if you multiply by this row on the left, you take 0 of this row plus 1 of this row. So we're just transposing how we've been thinking about matrix times vector in terms of columns. Got it? Well, you know what I'm going to ask next. This Taylor.
Is there any like geometric interpretation of that? Because isn't that the rotation by 90 degrees?
No.
Matrix?
No, that matrix is not rotation, it's reflection.
Oh yeah, reflect.
One of the ones was negative.
It's a reflection across the board.
It's reflecting across y equals x. You're switching x and y, so when you multiply it by any vector xy, you're switching x and y.
Okay.
So you put the first entry is what used to be the second entry, and the second entry is what used to be the first. So that is exactly the right answer. Great question. All right. Row operation type 2.
Multiply a row by 2.
Multiply a row by a non-zero scalar.
C times n.
So I need my matrix back again. 3, 5, 6, 1, 7, -2. All right? I want a mystery matrix that's going to give me C times the second row and leave the first row alone.
C
1,
times
0, 0, C.
Yeah.
Well, you want to leave the first row alone, so you want 1, 0 there.
0C.
And now 0C.
6.
Because that exactly takes 0 the first row plus C times the second row. 0C, 0C. Again, the shortcut is you took the identity matrix and you did unto it as you wanted the row operation to do unto your matrix. So you multiply the second row by C and leave the first row alone. So this is actually really easy to remember, right? If you want to do a row operation, do it to the identity matrix, and that matrix is going to do it to whatever you want. Last one. I've sort of blown the punchline. Add C times row I to row J.
Would you do?
So suppose I want to add, so think of this as the general example, and let's say this is row I and this is row J.
So 1, 0, C.
1, 0.
1, 1.
No, 2, C.
1, C,
1, 0, C.
Oh, C times.
Does that work? It leaves row I the same, leaves the first row the same. And what did it do to the second row? It took C of these plus this. Again, did you do the instructions to the identity matrix? You left I row alone and you added C times the ith row to the j. So you could say, well, I'm cheating because I'm only writing 2 by 2s. But do you understand what you would do with more rows and columns? So what am I about to tell you? I'm about to tell you that any row operations we've been doing can be encoded as a product of these kinds of matrices that we just did.
So like a linear transform.
So these matrices that I've talked about, these E matrices, these 3 kinds of E matrices, are called, E was not for echelon, but E was for elementary. Because multiplying by such an elementary matrix does what's called an elementary row operation, which is a single one of the row operations we've been doing. And so the story of the moral is going to be that you get an A to echelon form, or reduced echelon form, or whatever you want, by starting with A, and doing a row operation. Well, that's multiplying it by some elementary matrix. And then you do another elementary operations, another row operation, so you multiply by another elementary matrix. and then you do more and more elementary matrices until you're finally tired out, and you've done your last one, and you say, yippee, I'm done.
Make a regroup.
Regroup. Use associativity. This is the same thing as saying, what matrix times A gives me my echelon form?
All the E's.
All the row
Multiply
Some of them all multiple.
No, not some.
Multiply.
The product, you just group these, E1, E2, E3, ES. What you have to remember, however, you have to put them in the correct order. You have to go right to left,
And then,
because you're composing functions. Now, to get to the punchline here, I'll do some examples of this first thing on Friday. We'll do numerical examples of this. But to get to the punchline, when we did our algorithm, where we started with our super augmented matrix and we row reduced it, well, I can now write this as an equation that the succession of row operations here can be done by a product of e's. So I have the identity is what I get when I start with A and I do this product of e's. I'm just going to call that capital E for short. It's a product of little e's. I mean, the other e's. So what did I do? I multiplied this monster matrix by all those e's together. That means all the row operations were affected by multiplying by the product of these elementary matrices. So what does this equation say? Yes, it says E times A is I, but it also says,
that summation,
no,
or not
Summation.
summation, product,
the E, I'm multiplying by E on the whole thing, right?
Right.
So
It turns A into the identity,
I
and it
times
turns I
B.
into
B.
In other words, what's B?
what is the product?
The product of all the elementary operations that it took to turn A into the identity. That's the inverse, because you undid everything in A. So B is this product of elementary operations. Now, why does that prove that when I multiply B times, we already knew A times B was the identity, well, why is B times A the identity?
Then you just multiply by the ones in the opposite order.
No, easier.
No, you just, that equals,
B and E are the same thing. So B times A is the identity. No mystery. It just kept track of all the elementary operations when you did those row operations, and that means that it actually is the left inverse as well. Okay. So we'll do numerical examples of this on Friday, and then we will start talking about linear independence. So remember, I did tell you the test next Tuesday covers just through section 1, so what we're doing now is not on the test.
Oh.